All right. So, dot structures first. Now, you know how to do these. They're all in your notes. You could have just copied them, right? But I was hoping you didn't. The first two should have been pretty easy. Why? 1 and 2. They're just single bonds, right? So H bonded to an H looks like that, or that, or that. Any of those work. And I suppose you could have 2 X's as well. All right? So that's H. F2 looks very similar, except what? There's dots around it, right? Because each one has 7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Remember, these are covalent, they share. These are non-polar covalent molecules and bonds, right? Looks just like this. We're going to talk about this, talk about that again after the homework. So that's what it would look like for either one of them, really. Number 2. What's going on here? How's it a little different?
You mean number 3?
I'm 3, yeah, 3, sorry. Double bond, right. So O, double bonded to an O with 2 dots on each O, or if you did dot dot, XX, dot 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 dot. Technically these would be X's, but if they're all dots, that's okay. If you forgot the dots here on the O's not bonding, you would get points off. That doesn't work. Yeah, they have to do that. What these has? Okay. Questions? So, if you just memorize that, I'm fine with it. All right, but the reason it forms a double bond, 2 bonds, is to have a full valence shell, right? So both of them have a full valence shell. All right, nitrogen, what's the deal with that? Triple bond, 1, 2, 3. It doesn't matter, Shane, you with me?
Yeah.
Where these 2 dots are. Could be on top, right, bottom, top, left, bottom, doesn't matter. And 1, 2, 3, 4, 5, 6. That works too. Either one would be acceptable on a Regents or on the supplement. So if a Regents asks for an electron dot structure, sometimes they call it a Lewis electron dot structure. Either way is acceptable, with the bonds or with just the dots. Doesn't matter. Questions? O2 and N2, also nonpolar. Nonpolar bonds, and the molecule is nonpolar because it's very symmetrical. Shares everything equally. All right, what's next? CO2. Renee, what's that look like?
An O, and then 2 O's and C in the middle with the double bonds.
Like this?
Yeah.
Anything else?
There's electrons on the top and bottom of it.
How many?
2 on the top and bottom.
Like this?
Yeah.
Good job. That's it. That's CO2. All right, and again, this could be dot dot XX dot dot. You could have 4 dots here and here, but I'll just leave the dots. So that's CO2, nonpolar, very symmetrical. But the bonds here are polar. We'll talk about again why after the homework. Questions? Jake, what's water look like?
An O and 2 diagonal.
How about this? Can I do that?
No.
No. Where's your diagonal?
Bottom left and bottom.
Kind of like this?
Yeah.
Yeah, that works. And then do you have 4 dots? 2, 2? You should. Good answer. Yeah, oxygen has 6 dots. So you start with oxygen, 1, 2, 3, 4, 5, 6. H goes here, H goes here. It doesn't really matter if you draw it like I did here, or like Jake did, or like this, as long as you have 2 H's and they're not in a straight line. There has to be some sort of bend to it. Water is a bent molecule. It's not 90 degrees. It's 104 actually, 104.5. But that's water. Okay? Thanks.
You're welcome.
Good job. Moral support. All right. If you can't do the dot structure for water, you're in trouble. Yeah, that's basic at this point. 1, 2, and 6 should be easy. 3, 4, 5, I can understand you're a little trouble. Questions? If you circle them like the directions said, that's fine. That's just showing there's 8 around all the atoms except H, right? There's 8 around the O, there's 8 around the F, 8 around the N, 8 around the C. It's just hydrogen can only have 2. All right, now the fun stuff on the back. All right, take out reference tables, please. You're gonna need a periodic table and table E. All right. I'm gonna read all the answers from 36 up for the odd one. Then I'm going to go over 4 of them on the board. All right, 7, the answer is 0. Potassium metal, like let's say this was made out of potassium. That'd be a big problem. Why? If this was made of potassium, what would be the problem?
It's very reactive.
Yeah, it blows up the water. Okay? So that would not work as a water bottle. But the point is, solid metals, all right? Whether it's aluminum, iron, whatever, any copper, any of the metals, if this was made of potassium, it would be neutral. All elements and compound substances are neutral. I didn't tell you that. Sorry. That's not so relevant yet. Later in the year it will be. But number 1 is supposed to be solid potassium, which does not have a charge. When does potassium have a charge? In a compound. KCl. K is +1, Cl is -1. That was the point of the homework, practicing this stuff. Again, this we'll talk about later down the road, but because this is a compound, it needs to add up to 0. All right, so number 9, Na is +1, O is -2. I'm going to go kind of slow, but if you miss one, let me know. Don't fall asleep on me. Stay with me. All right, I'm going to read all the answers and then go over 4 of these slow up on the board here. All right, 11, Mg +2, Br -1. 13, K +1, Cr +6, O -2. 15, 15's tough. I will go over it. I'll go over 13 too. 15, N is -3, H is +1. P is +5, O is -2. 17, Fe +2, Cl -1. 19, Fe +2, O -2. 21, N +1, O -2. 23, N +4, O -2. 25, N +3, O -2. The O's are actually pretty easy, as you can tell. 27, Ag is 0. Again, you didn't know that ahead of time, so don't feel bad. 29, Ca +2, C +4, O -2. 31, C +2, O -2. 33, sulfur is 0. That 8 means it's 8 atom ring. If you remember the lab where we melted sulfur, we talked about that a little bit. 35, Mn is +2, S is +6, O is -2. All right. Now, I'm going to go over 13, 15, 29, and 35. Because those are like 4 of the hardest ones. If there's another 1 or 2 you want me to go over, let me know. Silas.
For the ones that most compounds that you said were hard, aren't they on table E? So you can just look at that and do that.
Yep, that's how I'm going to teach it. So if that makes sense to you already, great. But I'm going to show it to everybody. Yeah.
So I like the compounds, I just took the charge of the compound.
Yeah, that's what I did.
Yeah, that's what I did too.
Would that be wrong? If I
Yes.
just charge the compound?
If you look at the samples and what I said yesterday, I wanted each element. So if you look at the samples, they were doing each element. And then yesterday we went over 14, right?
Yeah.
And then, did we go over another one? Or was it just 14?
26.
Yeah, so we went over a couple. So, yeah, I intended every single element I wanted you guys to label. So if some of you didn't do that, you were just confused. I know you didn't do it on purpose. So if I wasn't clear, I apologize. So just fix it for tomorrow. You can do the rest of these for tomorrow anyway. So, so tomorrow, if you didn't do it right, then just fix it for me. And then you're doing all the even ones for tomorrow. All right. So that's okay. Show me tomorrow, or fix it. Any other questions before I go over those 4? Okay. So 13. Here we go. K2CR2O7. Now, stay with me. I feel like it's really warm in here. You probably just had lunch. You're feeling a little sleepy, but I really need you to pay attention. There will be something like this on the Regents. It might be multiple choice, could be short answer, it could be part of another question, but this is a skill you need to know. And I think it's a skill everybody can learn. Everyone can do this. You just have to pay attention if you're confused. And if you're not, pay attention anyway. All right. How do we do this? Well, I need to look up the charge for all 3 of these on the periodic table. I'm going to show you 2 ways to do this. Here's the first way. Everyone go to K. What is the charge in the top right corner? +1. Is there any other charge in the corner? No. So K has to be a +1. All right. What about CR? Yeah.
There's 3.
2, 3, and 6?
Yeah.
2, 3, and 6. So we don't know. It could be a 2, a 3, or a 6. What about oxygen?
-2.
It's got to be -2. Now, I already gave you the answer. Everyone knows it's 6. I just told you. But here's how you would do it on your own if you're confused. So, like these 2 were telling me, they did the charge overall. So, what did you guys write? 0?
No.
Just
Compound
-2.
equals -2.
No, compound equals 0. All compounds are neutral. You're talking about this thing.
Yeah.
Okay.
That's
All
what.
right.
That's why
And
I
that's
wrote
it.
what
'Cause you had
you
to
were
take
talking
the E.
about, but you sounds like you did it right.
I sorted it,
Okay.
but also did it.
Alright, so let's just get everybody on the same page. So what I want you guys, everyone here to understand is this is a compound. So if you see this written on the test or on the board or whatever, so all of this must equal 0 overall. These little numbers on top called oxidation numbers or charges will not necessarily add up to 0 because the subscripts factor in. That's what I'm trying to teach and show you. So let me go through this one and see if everybody is good. And we have 3 more practice anyway. So let's just finish this and then we'll see where we're at. All right, see if you understand what I'm saying. So we have 2 Ks. That's a +2 overall. All right. The charge on K is +1, not +2. That's just the overall charge 2 Ks provide. So +1 is the oxidation number or charge, same thing. This we don't know. What's the total charge here, Tyler? Stay with me.
14.
You look tired.
I am.
-14. Questions so far? Like where I'm getting those numbers from. 7 times 2. There's 7 of those. Each one's -2, so that's -14. Okay. So all of these numbers down here must equal 0. If I add these 3 numbers, they must equal 0. Not these 3. They don't factor in the subscripts. These do. This is the total charge. This is the charge you'll find on the periodic table in the box. So the reason this is +6 is because there's 2 of them. So 2 + 6 is a +12. Now 2 and 12, that's 14 minus 14 is 0. So that's why CR is +6. So on a Regents, they'll give you this and say, what is the oxidation number on CR? And they'll give you +2, +3, +6, and some other number that makes no sense. One that isn't on there. +2, +3, +4, +6. Those are your 4 choices. You need to do the math, figure it out, that it's a +6. Now the other way to do it, and I think it's what you 3 are talking about, and Quinn was saying something too, is I'm going to split this. I'm going to say, all right, I know K is +1 from the periodic table. And I know this is on table E, or maybe you don't, but I'm saying it's on table E. And that is called the dichromate ion, and this, 2 CRs and 7 Os, has a -2. Not with the K, just the CR2O7 is -2. So you do the same process, except it's like maybe easier. You're just dealing with 2 numbers. So this is -2, that's still -14 down here. So again, what is this? It's going to be +6 because that's going to be +12. 12 and 14, -14 is a -2. So if it's giving you the ion, you still do the same exact math, same process, except just this ion is -2. You throw in 2 Ks, now it's going to add up to 0. but all the numbers will actually be the same, just depends on how you do the problem. So, is this making some sense? So that's just one. That's just one example. We're gonna do the other three. All right, and I hope at this point, like this one, is easy. I hope that's easy. If this is -2, this has to be a +2, you move on. That should be easy, I hope. These are harder, I understand. And now at the bottom, all the ones with the arrows there, pointing to the charges, that's just like this without the K. That's just the ion, and we're gonna do those for homework as well. I didn't really do a good job teaching that, so I'll explain it more today, and then you can show me tomorrow, you'll do it for homework. All right. So let's do 15. 15 is the hardest one on here. Why? Well, that's not true. I'm sorry. 28 is the hardest, but 15 is close.
There's 2 polyatomic ions.
Yeah. There's a lot of subscripts, 2 polyatomic ions. So here we go. Everybody awake? We're good? Up here, focused? Barely. Well, that's better than not. Oxygen is the -2. We all know that at this point, I hope. It's the only charge in the box. Okay, do me a favor. Look at N, H, and P. What do they all have in common? I'll answer that. They have more than one charge. H has a +1 or -1, right? H is +1, -1. P is hold on, -3, +3, +5.
Yeah, I agree.
Yeah.
And then N a whole bunch. -3, +1, +3. There's a whole bunch there. I don't know what all of them are, but N has like 8 or 9 or something like that. So we don't know which one these three use. So this one's really hard. See, with K and CR and O, we know this is +1. We know this is -2. So we only have one to figure out, like the last problem. This one's harder. But I will tell you this. It's safe to assume H is always +1. That is not the case, so I'm not going to completely lie to you. Sometimes it's -1, but it's such a rare occurrence, I wouldn't really worry about it in regions. When it happens is this: metals with hydrogen, metals lose, non-metal gain, ionic transfer. That's the only time H is negative. You're really not going to see that. So let's not worry about it. So we're going to say, all right, H must be +1. So now that's better. We know 2, we don't know 2. And now what Caitlin was saying, these are 2 polyatomic ions. So I would prefer not messing around with all of these numbers. I'm going to split it. What does that mean? I'm going to look these up on table E. This is +1. All the N and 4H is +1. And then the PO4 is a -3. These are on table E, ammonium and phosphate. This is just like the bottom of the sheet. So pay close attention because you're going to do the bottom of the sheet for tomorrow. All right, so we're doing the same thing we just did, except this adds up to +1 and this adds up to -3. So again, eyes up here, stay with me. H is +1. So what does N have to be? So all of these atoms, there's 5 of them, 1 N and 4 H's, add up to a +1. Well, if I have 4 +1s, that's a +4. So what's this have to be? -3. Because -3 and +4 equals +1. Again, the top charges will not necessarily add up to what you want. That's fine. It's the total charge that helps you figure those out. So you got to kind of understand both of those scenarios. All right, over here, O is -2. So what's the total charge on the oxygens? Right here.
Positive.
-8.
Yeah,
-8. You with me?
well, I was thinking of P
Hold on.
first.
Okay, don't think P. You got 4 -2s. Does it make sense that that's
Yeah.
-8? Good. So now P must be positive, like he's about to say, and it's +5 because that adds up to a -3. So now you're done. N is -3, H +1, P +5, O -2. The reason this is important is it helps you understand who's losing, gaining, sharing electrons. Between nitrogen and hydrogen, nitrogen is going to have a higher electronegativity. It tends to be more negative. That makes sense. Same thing here. Oxygen tends to be more electronegative. It's going to be more negative. That makes sense. So the bonds in here will be polar. N wins the pole, O wins the pole. That's part of what's going on here. Also, it balances out to 0 overall. This compound's neutral. Okay, I would not worry about that on a Regents. Number 13 is about as hard as it gets on a Regents. Okay, next, 29. You should have a better feeling now on how to do this. Calcium on the periodic table, what's the charge?
Plus 2.
Plus 2. We know oxygen's minus 2. Eyes up here. Everybody look up here. Jake, stay with me. I have 1 Ca, that's a plus 2 overall. I have 6 of these, that's a negative 6. All 3 charges must equal 0. Therefore, this must be a plus 4, because 4 and 2 is 6, 6 minus 6 is 0. So that's how we do 29. I know I went faster, but it's easier than 13 and 15. There's no subscripts down here on the C. And then 35 is a little bit harder than this one. MnSO4. Okay. How many charges in the box for Mn? 4. 2, 3, 4, 7? Okay. Here's how we do this one. So again, eyes up here. I'm going to split this apart. Mn over here, we don't know. But I do know SO4 is a minus 2. This is on table E. Sorry, that O should be a little bit bigger. SO4. I know this is on table E, so all of this must equal negative 2. Well, if oxygen's negative 2, that's a minus 8. So this must be a plus 6. That adds up to a negative 2. So now I know S is plus 6, O is minus 2. That's how I know S is plus 6. I can't do that up here. It's too confusing. There's too many options. So I do it with the ion here, and I know it has to be a plus 6. So now, again, eyes up here. This side of the molecule, MnSO4, this side of the compound, is a negative 2. So if MnSO4 is neutral, this must be a plus 2. That's what Mn is, plus 2. That's how we figure that one out. So you got to use your periodic table, you got to use table E, and then, you know, this is going to sound silly, but figure it out. You have everything in front of you, you just have to label things correctly, do the math correctly. Big problem, a lot of kids, they see something like this. No, I'm sorry. Something like that. How many O's are there?
6.
9. There it is. No, I'm glad you did it, because that's the mistake. Kids will go, oh, that's 6 O's.
I didn't see the bottom.
That's all right. So that's 9 O's, right? So that if it's a negative 2, that's a negative 18. That, you know, so that's where it gets confusing when you have a lot of numbers, subscripts, parentheses. So just be careful. All right. The good news is something like this, KMnO4. That's a pretty common Regis question. They're going to ask, what is this? So you only have one subscript to deal with. That's a lot easier than, you know, something
I have a
with.
question.
Yes, sir.
Could you also do like Mn plus 4 and then S4 plus 4 and O, like the O negative 2 thing? That still equals 0.
Yeah, actually, from your perspective, you're right. But, no, that can't work. Here's why.
Why?
Here's why. This is called sulfate.
Yeah.
Sulfate is a set polyatomic ion with a negative 2 charge. So I know an S with 4 O's always, every single time in chemistry, in reactions, in real life, has a minus 2. Always. And if we know oxygen has to be a minus 2, there's no other charge this could be except 6. Because that's negative 8 and positive 6. So this SO4 as a team, as a unit, can only be a plus 6 and a minus 2. Yes, that works. I totally agree with you. That adds up to 0. But that's not correct for this compound because that's sulfate, not sulfur.
So how would you know the difference between if it's gonna be like sulfur and then oxygen?
If it's not SO4 or here's a crappy answer. Experience. Like the more you see this, the more you just get used to it.
That's just stupid.
It is, because it's hard for me to really, there's nothing I can really teach you to fully get ready for that, so that's why I stress use table E. If it's on table E, use it, and then go from there. Because you're right, it's hard, it's confusing, I get that. From your perspective, I totally understand why
I
that
did
is.
the first way, but.
That's confusing, I get it, you know? Typically, if you see these, they are on, this one's on table E, right?
Yeah.
Yeah? Okay.
sulfite.
Yeah, sulfite, right? Sulfite, sulfate. Typically, S with O, it's almost always a +6. But again, how do you know, right? As a Regents student who just learns this, you don't. So use table E as the best thing.
Alright.
Okay. But, that's a great question. All right, take your notes out. Oh, and to be clear, do the even ones up top. The charges down here, just do the odd ones again. So if you did them all right already, then you're done. If you were confused, go back and fix it. Okay? So do the odd charges down here and the even compounds up here. Am I being clear with that? You know what I'm asking you to do? Yes? Yes? Any questions? Don't do 51. That one's kind of weird. Everything else should be fine. All right. So notes. All right. Yesterday we talked about single bond is the longest and weakest. Double bond is a little bit shorter, stronger, and then the triple bond, right? The three pencil pieces here, the shortest and the strongest, right? You wrote that down, and we're gonna move on. I was gonna show you something on here, but I'll just use these instead. Plus lab is really helping with that, I hope. I feel like we haven't had lab in forever, my lab. We didn't have it yesterday. What's today?
Wednesday.
Yeah, so we had lab last Friday, right?
What?
Yes, your level.
Oh yeah, I'm gonna have a band lesson
Oh,
tomorrow
yeah.
in lab.
So that means you and Zeke are too?
Yeah.
So that means it's gonna go over a week since you guys had lab. That's yeah. All right, write these 4 molecules in your notes. Br2, CO2, CF4, and I2. I will bestow some of this stuff on some of you.
What? You just skipped me. I should skip me.
I gotta spread out the fun. Renee looks like she needs some fun today. Yep. I guess, Shane, you know. Oh, Denonica wants that.
No, I don't.
You're
Just
good,
wait for
Mike.
one day for Shane just to.
Yeah, I was about to say, you.
Yeah.
He's like, yeah,
I do know.
no, that one looks cool.
I don't think it would be on me. Maybe. I don't feel like I'd give him less a hard time.
You just had enough.
He's had enough of everybody. Yeah, but I think he knows too, everybody likes him. Why could you not like Shane? Well, Shane's the man.
He's entertaining.
Alright. He's good, good person, good
Yeah.
heart. Alright, okay, so you have a decision to make here. You can talk to somebody about it. Talk with your people. Which two, actually let me ask you this question, sorry. Polar or non-polar, these 4? All of them are non-polar molecules, but 2 of them have polar bonds and 2 of them have non-polar bonds. Which are which?
I would think we're.
Oh, talk to somebody and think, and then I'll go over after class. So take a minute, discuss.
You know, it's liquid.
CO2 and CO4. The other two
Flipped over it and now it's liquid. Doesn't matter. Doesn't matter. Oh, no.
Iodine and rhodium. That's a building.
Oh, that's a problem. Oh, that's
They
right.
have, are not
CF4 and CO2
No, they're symmetrical. They just
I
have.
mean, yeah.
They have polar bonds.
Yeah, it's polar.
Quinn or Will, is there any other period you guys could do that, or is that just the way the schedule is?
That's just the way the schedule is.
I mean, I'd rather be lab than class.
I'm gonna be totally honest, she probably, very good chance she's gonna cancel it.
Yeah, no, she cancels like at half the lessons.
Alright,
So we might be.
but you've never had one canceled before, not for me, have you?
Not, I
With
have
you, but
not with
I've
you.
had many.
Alright.
Yeah, no, we've had
It's
many
not,
canceled.
listen, you guys get caught up, not
Yeah.
too worried about it, just losing 3 is kind of
Just come here for
Alright, Shane, just to get you caught up to speed here. These are all non-polar molecules. Hold them up. You guys each have one. Oh, someone's.
I get ready to go.
You just want.
Ride. All right, ride. All right. So, Renee and Fred, get a little bit higher there so everybody can see it. Okay. Shane, which one's which? Put you on the spot.
Like red is
I'm telling you, it's just. Come on, Shane. Rebecca, see at 4.
Very good. See, Shane's on the money here. That's what she's holding. Yep.
I don't know.
Now these two can be interchangeable. So what's Tyler holding?
CO2.
CO2, very good. And then I'll get you off the hook here. Go ahead, put them back up. Put them back up. I want everyone to be able to see these. That's why I have you hold them. All right, so Fred and Renee, you're holding these two. All right, Quinn, sounded like you know what you're talking about over there. Which is which?
I2 and BR2 are non-polar molecules with non-polar bonds.
Okay, you put yours down, you put yours down. Hold it up again. It's good for your shoulder. Up, high. Come on.
I can't see in the back.
See, Will can't see it. Will can't see it. All right. So, when you have a green and a yellow and a yellow, what's the stick? You can put them down now. A single bond, right? So, if Br is bonded to Br, what's the electronegativity of Br? I think it's.
There's no difference.
I think it's. You're right.
That's why-
I think it's 3 though. I think it's.
Yeah, it's 3.0.
All right, and I 2.2. No. 7.
2.7.
2.7. Okay. So, and like, get here, chuck that here. So, like, Kaylin was saying, so because it's bonded to itself, there's no difference in electronegativity. So, if there's no difference, that's literally the most perfect way electrons can be shared. They're going to be right in the middle. Nobody's winning that tug of war. So, any Hakelbrief, right, the diatomics, these are non-polar because they're symmetrical, but the bonds, the stick here, also non-polar. That's the only 7 that exist. And again, Quinn asked that question, you know, what if this one was carbon and this one, what was it? Or hydrogen
It
and
was
phosphorus?
hydrogen and phosphorus.
Yeah. So if it's 2 different elements and they happen to have the same electronegativity, technically someone still will win slightly. The only way to be pure nonpolar is a diatomic. 2 are the same. Again, that's because it's bonded with itself. So these 2, hold those up. Okay, the springs here and the sticks over there, what do the springs represent? Double bonds. So there is a difference here. Carbon is 2.6, oxygen is 3.4, 2.6, 4.0. So the bonds are polar because somebody is winning that tug of war. In this case, the oxygen wins both directions. They cancel out. They cancel each other out, so overall the thing is nonpolar and symmetrical. But the bonds themselves are actually polar. Same thing over here. You have your 4 Fs. All 4 Fs are pulling equally, so each bond, fluorine wins, fluorine wins, fluorine wins, fluorine wins, but because it's balanced, it's nonpolar as a molecule. But again, the bonds are polar. I don't make a big deal out of writing a lot of notes for this. I explain it now. You use the models in lab, and hopefully you see that. Basically, the only ones that are nonpolar bonds are the ones bonded to themselves. If you remember that, you're in good shape. I'm going to add that to the lab. So I know you have like 6 things. I'm going to add number 7. Number 7 is going to be identify the molecules in lab that are nonpolar with polar bonds, nonpolar with nonpolar bonds. So if you're following me here, shouldn't be a problem. All right, and that's going to be something we'll do in lab. So I'm gonna leave that. We're done with this. We're almost ready to move on to metallic bonding. Toss it gently. These springs just snapped. You got it. I'll catch you. Good. All right. Well, actually, this morning, who was it? Somebody sitting over there threw it, and I was standing here, and Talia sits here, and it like went right over her head and face. It was kind of funny. Who was that? Who threw that? That's Amanda. What's up, Jake? That's
Olivia.
Reagan.
Reagan.
It might have been Reagan.
Oh wait, what
Yeah,
period
I
are you
was
talking
gonna
about?
say
It might have been Reagan. I don't know. But anyways.
Do you want this one?
Oh yeah, right. Okay. All right.
Very good.
Now. Write this in your notes here. Properties of ionic and covalent. What's the other name for covalent? Maybe I didn't tell you. I thought it was. Didn't we do a practice? Did we do a practice problem yesterday? We did one, didn't we? It was 4 choices. It was like, which of the following is element X?
What?
Yeah, but it was number 1.
Oh, the.
I'm not gonna be able to find the question in time. I'll show you tomorrow. I'll write myself a note. Another word for covalent is molecular. Have you ever heard me say that?
No.
Okay, fair enough. Period 6. Question. I'll find it. There's a multiple choice question that says, Regis question. Which of the following 2 elements creates a molecular compound? And if you don't remember or know, those mean the same thing. You don't know how to answer the question. So we'll do that tomorrow. All right. What have you learned here? Let's separate. We'll just kind of start this and finish it tomorrow. Let's just. You know what? You can pack up actually, but out loud, let's talk about it. So while you're packing up, what have you learned in lab?
Ionic is stronger.
Ionic strong,
But
covalent.
dissolves in water.
Well, hold on. Ionic strong, covalent, weak.
Ionic dissolves in water.
Ionic dissolved in water, but didn't some of the covalent dissolve in water?
I think
Yeah.
one
One of them.
one did.
Do you remember which one?
I think it was
Sugar. Yeah,
dextrose.
All right, we'll talk more about it tomorrow. Yeah, dextrose.